Great. Well, thanks so much. It's a pleasure to be here. This section of the webinar is really aimed at students and people who may be expert in different technical areas without a traditional power engineering background. So what I like to do is give a little bit of context for different kinds of grid measurement data, and then see how PMU or phasor measurement unit data, also known as synchrophasors, fit into that context, and develop a little bit of a physical intuition about what those data mean, and how we can start to sort of feel what they tell us about the way power flows in the electric grid. So for some of you, this may be very basic, but we want to make sure that, we cover those fundamentals. Sometimes there's still, it's hard to build an intuition around this. So sometimes even more experienced students have questions that hopefully we can discuss. And it's really great to be sharing this morning with Kevin Jones, who has a lot of experience working with PMU data in the real world. So between the two of us, hopefully we can answer your questions. So just as a really high-level overview, there are different kinds of sensors throughout the electric grid at different levels, with different kinds of resolution. It's interesting to think about the fact that most of the legacy electric grid as we know it has really been around for over a century. So it had to be designed to work without a whole lot of measurement or communication, right? Electric grids could be operated in the days before there was even telephone lines between different power plants that were coordinating. So it's really quite phenomenal that the lights stay on even without detailed monitoring and sort of high resolution observation and control of different aspects of grid components. But of course, as things get larger, more complicated, and we have higher expectations on performance, and also we now have more interesting renewable intermittent resources contributing to the mix, there really is a need to understand things in greater detail. So there has been this trend toward higher resolution in time and space for measurement. For many, many decades, there were just measurements at power plants and at the customers. And then in the sort of late 20th century, there was a proliferation of SCADA instrumentation at distribution substations and then out on distribution circuits. Transmission substations had been instrumented, a little bit earlier, but it was not really dense measurement, not really rich measurement. It was sort of a really rough sense of voltages and currents to get the big picture of power flows. As we find ourselves operating the grid sort of closer to its limits, and we try to be more efficient and economical. And also we want to manage resources with higher resolution. We need more refined data, right? And so in the spectrum of different types of sensors, the phasor measurement units are a really important step because they actually show what we'll explain are the state variables of power flow in the grid. So they show us magnitudes as well as phase angles or very precise timing of voltages. And they also measure currents. Now, for context, I want to mention that, you can go farther in this direction with continuous point-on-wave data. So point-on-wave can tell the entire AC waveform in much greater detail, whereas the PMUs are really an abstraction that we'll describe. I really recommend this report on the NASPE website by Alison Silverstein and Jim Fallum that talks about these different kinds of measurement data, and particularly point-on-wave data. just sort of for a visual here to put this on a scale of different orders of magnitude in time, what we're looking at here are we're focusing mainly on the time frame sort of around a cycle, right? 1/60th or 1/50th of a second. And there's very different questions that you can ask about what's happening in the electric grid, and very different options for control or decision making that you can exercise at different timescales. And generally, you know, we talk about steady state power flows at these longer time scales where traditional monitoring is often plenty. So SCADA instrumentation reporting every few seconds can give you a good enough sense of, you know, how is the load, for example, relative to the capacity of the system. Are you not going to overheat something? But then if you're looking more at the dynamical response and see how things change, and also see what happens when things aren't exactly like in the textbook, when you have disturbances that are, you know, causing things perhaps to oscillate, or when you have faults, those are the situations where you really need to zoom in closer. So for point-on-wave data, traditionally there have been digital fault recorders that record the entire AC waveform, but just for a short period of time and locally, to understand the fault locally, to make a decision, for example, about whether to open a circuit breaker. But that information hasn't been historically correlated with other locations, right? So when we talk about grid intelligence, really an important piece is the correlation between different places. And so I want to give you an example just with these micro PMU data of the benefit of even just having voltage magnitude data that's reported many times per second, as opposed to once every 5 seconds, to sort of appreciate the texture that you get to see. So in this picture, we have 2 micro PMUs at different locations in the San Francisco Bay Area. The blue one is in Berkeley, the red one is in Alameda. They are separated by a 115 kV transmission network. But you can see here that there's a fault event, and for each location, I should say, there are 3 phases, ABC phases. So there's some fault event somewhere in the area, and both of these PMUs are picking up the voltage sag that came with that fault. So one important point here is that high impedance faults, which are dangerous, they are faults that can be caused by any number of things making contact with electric conductors that they're not supposed to, whether it's tree branches, animals, and what have you. They don't draw enough current to trip a circuit breaker or blow a fuse, but they can start fires, which we're now very keenly aware of. And being able to recognize where that's happening can point you to a faulty piece of equipment or a tree that the tree trimming crew missed, to be able to take care of that situation before it starts a fire. So you can see here in this time series stream that with 120 reports per second, you can get a very detailed profile of how the voltage dipped down on the 3 different phases and then recovered. And without these PMU data, you might not know that anything happened, right? This could have been a tree branch or an animal somewhere. No one would be the wiser. So identifying that high impedance faults are there, diagnosing why solar inverters tripped offline is another application here. Or you can see that there's this pattern of how the 3 phases relate to each other, and you can actually use these correlations to line up what's phase A, B, and C. And Mohini will talk about that in next week's part of the webinar. You can determine connectivity of the system as well. So there's a lot you can do just with high resolution magnitude measurements before we even get into phasors. But so what are synchrophasors? What's this phasor representation about? I'm using an analogy here of a photo of me and a stipple portrait that's an abstraction. It's a simplification. It's a way to get sort of a general character across of the thing you're representing with less data, right? It's easy to print this stipple portrait with a small amount of black ink. It doesn't show you everything, doesn't show you skin color. We make assumptions about what variables are held fixed. When we simplify and abstract, it's really a lossy compression of information. So you can't tell if, you know, I'm red in the face in this picture. If a person were illuminated with different color light and then you tried to do the stipple, you would get maybe an unrecognizable picture. So with electric waveforms, we can abstract them into phasors on the assumption that there's a kind of behavior that we all agree is there. Namely, we assume that there's a sinusoidal waveform, which we can then represent in terms of just two quantities. And those two quantities are the root mean square magnitude and the relative timing of the sine wave compared to a reference clock or compared to another sine wave. So graphically, if you're not a big fan of math, this picture is kind of all you need to translate the height of a sine wave. And here I've actually shown the full amplitude rather than the root mean square that we use by convention in engineering. But either way, it's a measure of the height of the curve in green and then a measure of the timing relative to when somebody pressed the stopwatch and said, this is time equal to 0. And that's in red, and that time dimension becomes an angle. And so in the complex plane, where the imaginary number is the square root of -1, it's the thing that can't decide if it wants to be positive or negative, so it just wiggles. In that plane, we imagine the phasor is rotating, which is a representation of this sinusoidal sine or cosine waveform. So if you're not into the math, you may avert your gaze for the next slide. Just for those of you who are reviewing or are studying power engineering, the way you get to this notation is you basically imagine that the sine wave is a projection of a helix, of not just a sine wave in one dimension, but a two-dimensional sine wave, just like a corkscrew, right? So if you take your wine bottle opener and you look at that corkscrew, any direction that you look at it will look like a sine wave. So you're writing the voltage, could also be the current, as a function of time, rather than just a cosine. You say, well, let's suppose that cosine is just the real part of a complex expression, which includes the cosine and an imaginary sine of the frequency omega times time plus the phase shift Greek letter phi. J is the root of -1. So we haven't changed anything. We've just said, well, the cosine is just the real part of this expression cosine plus J sine. Then we can use Euler's equation to say, well, that's equivalent to a complex exponential. And that complex exponential is implicit then in the phasor notation that we use. It has a rotating part, which is the e to the j omega t, and e is the base of the natural logarithm. And if you're not familiar with Euler's equation, you need to be, because it's the coolest equation there is. So the e to the j omega t is a part that rotates around in a circle, and the e to the j phi is the part that tells us about the relative phase. So the e to the j phi is the metric that really places the phasor in the complex plane. What this amounts to is you taking your wine bottle opener, you're taking your corkscrew, and now you're going to turn it around and look at it from the end so that what you're seeing is a circle, right? So we're going to eliminate the time dimension. We're going to ignore the e to the j omega t, because we'll say, well, everybody knows what the frequency is. It's just 60 hertz or 50 hertz. So we won't talk about that. And then we have just the magnitude and this exponential e to the j phi, which we write in a shorthand with an angle symbol. So we've basically said there's two pieces of information to know. Everyone already knows the frequency, so it's that time shift and the magnitude. We'll come back later to what happens if we didn't know the frequency. But so the snapshot in time, so on the left now we're looking at the corkscrew from the end, allows us to very conveniently compare different sinusoidal waveforms. So the gray one is 90 degrees ahead of the black one, and we have this implicit rotation in the counterclockwise sense that says, yep, the gray one is 90 degrees in front, and it's a little shorter than the black one. So that's a way graphically to very easily represent the relationship of different sine waves. And, you know, power engineering textbooks are full of phasors because it's so much more of a concise representation. Now, a short digression. We have three phases in our standard AC system. And at the transmission level, typically it's a pretty good assumption that those three are balanced. So you could measure just one of the three, or you can give what's known as a positive sequence representation, which is basically a kind of average of the three phases. And a lot of the transmission level PMUs do that rather than reporting back all three ABC phases. So if you're not familiar with that term, the positive sequence just means it's the part of the three, a component of the three that has kind of the right ABC sequence and represents them as all being the same magnitude and exactly 120 degrees apart. If you look at distribution systems, you will find that they can be really imbalanced, and then sometimes it's necessary to look at all three phases explicitly, or to think about the three different mathematical components that are positive, negative, and zero sequence. So that's another fun adventure. But coming back just to the, simple single phase representation, let's think about the time dimension here. So the AC frequency is never exactly constant, right? So when we are looking at the phase angle of one particular sinusoid relative to when we decided to press the stopwatch and say this is time t equal to 0, we will find that, well, that relative angle is going to be decreasing or increasing depending on whether the frequency is greater than or less than 60. So what that means is when we look at a time series picture of phasors, we see this like characteristic, sawtooth kind of pattern, where in the first part of this upper graph, we have the phase angle increasing, not at an exactly constant rate, but, so this has the frequency being slightly greater than 60. And then at some point right in the middle, the line is flat, and when those degrees of phase angle stay constant, that means the frequency is exactly 60 hertz. And so the math that calculates the phase angle reports a constant number. And then the frequency in this system drops down a tiny bit below 60, and so that's when the degrees go down. So one of the things that you have to do when you're using PMU data, first of all, is to unwrap what is going to go up or down to 360 degrees and come back around at 0, right? Really, you don't get physical meaning from a single phase angle report from a single PMU, because it tells you what the frequency is, but it doesn't tell you anything about power flow. To understand how it kind of physically reports what's happening in the grid, you need to compare it to a PMU measurement from somewhere else. So in the lower picture, there's two different PMUs, and we're comparing the voltage phase angle between the two of them. And you can see one is a few degrees, the blue one is a few degrees ahead of the red one. So that corresponds to a meaningful steady state power flow between those two places. To do that, you need to use the same clock, right? You need to compare your measurement of the waveform to the same time reference. And it was GPS satellites that made that economical, short of every PMU having a super fancy atomic clock built in. And, chip scale atomic clocks, I should say, are actually getting cheaper and are becoming a feasible alternative to GPS timestamping that security experts are, thinking about, because GPS is not completely invulnerable. But it was the proliferation of GPS data and having GPS receivers that are affordable, that could be built into PMUs, that made it possible to actually have a geographically spread out network of PMUs that are relating the voltages and currents, but in particular the voltage angle between different locations. So the clock has to be pretty good. And this is depiction of the time precision criteria for a micro PMU, which we developed at Berkeley with Power Standards Lab under an ARPA-E project starting in 2013, to see just how precise could we make a PMU measurement in terms of having the exact alignment of the clock between different devices. So that timescale gives you a little sense here of where a degree of phase angle separation sort of fits in. To distinguish power flows on the distribution system, really you want to get down to 1/10 of a degree, which is about 4.5 microseconds. So your clock accuracy and your timestamp has to be better than that in order to meaningfully resolve this. The analog samples in the micro PMU are at 512 per cycle. So that comes to about 30 kilohertz or so. These vary a little bit across PMUs, but you really have, when you talk about samples, you have to be very careful whether you're talking about analog samples of the waveform, like in a real photo, right? Or whether you're talking about the data frames that are reported, which are like the dots that are reported. And these are, depending on the PMU, somewhere between once every other cycle to twice per cycle. And so hopefully that's a useful reference for you. Speaking of precision, and I think precision is a better term than accuracy, because there's many things we don't know. For instance, oftentimes PMUs make measurements through voltage or current transformers, and those instrument transformers are not exactly accurate, right? So the quality of the measurement, the accuracy of the measurement, is only as good as the transducer or the weakest link in the chain. But the precision just refers to the ability to resolve differences. And there's a standard referred to as a total vector error that's been used in the industry that says, well, basically you should be within plus or minus 1% of the magnitude of that vector in the complex plane. Now, it's interesting when you draw this circle of 1% magnitude around the tip of the arrow and say, your measurement should land somewhere in the circle of the true value. That has two different dimensions, right? It has a time dimension, sort of in the azimuthal direction, and a voltage or current dimension in the radial direction. And if we zoom in on that, say, well, what does 1% total vector error tell us about the time resolution here, or the angular resolution? We get that it's basically about a half a degree of angle. So one conclusion is that the 1% total error, which is perfectly fine for looking at power flows in large areas, doesn't really tell you enough about steady state power flows on distribution systems. I want to kind of shift gears a little bit and talk about the physical intuition for what these phasors tell us. This may be old hat for many of you, but it's important, I think, to sort of have a visual of how different components in the electric grid stay locked in synchronicity. And so what is synchronous here? Well, it's rotating machines that are synchronous. And the analogy in this picture is from, an old-fashioned factory where different machines are linked, just analog mechanically, by this belt that's connected to a common shaft. And so we have a shaft running along the ceiling that is a way to distribute power, because you could have a motor that is driving the shaft, and then you can have the shaft driving other motors. The belt can be pulling in either direction, and it could be either taking energy out of the common shaft or putting energy in to that rotation. So since everyone has that reference, that is the system frequency, right? It's the rotation of that common shaft. And in the electric grid, there's an electromagnetic set of forces that take the place of just the belt and friction and mechanical pulling. But this makes it very intuitive that you can, if the balance of power generation and demand is off, then the whole thing is going to speed up or slow down, right? Which is what we observe with the system frequency. But more so, thinking about how we conceptualize this phase angle, is that the shaft really has a little bit of a twist in it. And, if it's steel, it's going to be quite rigid and not twist very much. But if it were a rubber shaft, you could really visualize how it could be twisted. And in the place where you're driving it forward, it's going to have a little bit more of a forward angle twist. And in the place where the shaft is pulling a heavy motor, it's going to be held back a little bit. So that is, I think, a nice mechanical analogy to the voltage phase angle, which is going to be twisted as you transmit power across a transmission line, which is now our analog for this common power reference or resource. And in fact, if you measure exactly the timing of your voltage phase angle at one end and the other end of a transmission line, you find that they have to be, by the laws of physics, shifted or twisted a little bit by what could be a fraction of a degree or quite a few degrees, depending on how far you're going and how much power is flowing. So this is from FNet, which is a great resource for sort of wide area visualization, from UTK, University of Tennessee at Knoxville. And it gives you a visual of a gradient, like a heat map of a voltage phase angle, and they show you this online in real time, of where power is flowing from one place to another. So this should be kind of a visual reference of the places where more power is being produced. That's where the phase angle is more forward. Now, again, if you're not into the math, you can avert your gaze. But for many of you, this will be a good review or an interesting maybe prompt to read more about the actual power flow equations in a large network. And what's really cool is that for any location, any node I in a network, you can write the real and the reactive power, P and Q. So the reactive power is power that's circulating because of inductances and capacitances in the system. That's not doing useful work, but that's essentially sloshing around because the physics demands it. And we need to account for both real and reactive power, and those can be written as functions of the voltage magnitudes and phase angles at every node I in the system relative to every other node K. So the voltage magnitudes and phase angles are the state variables that determine power flows everywhere. If I give you the voltage phasors at every node in the system, the state is completely described unambiguously. On the other hand, if we have the real world problem of knowing where power is injected and demanded, if we then want to solve for what are the voltages, the magnitudes and angles, that actually is a very tricky problem, which we have to do numerically. There's not a closed form solution, and there could be more than one mathematical solution. So power flow analysis is a really interesting field. It's all based on the voltage phasors being that variable that drives the power flow. So for real power flow between two locations, a really useful approximation, great rule of thumb, is that it goes as the product of the two voltage magnitudes at the two locations divided by the inductive reactance X in between. And that's, we're assuming, is pretty much describing the impedance of the transmission lines in between. We're assuming here that transmission lines don't have much resistance, which is a good assumption because they tend to be pretty hefty chunks of, aluminum and steel. They're made to not be too lossy, but they have magnetic fields around them, which makes them inductive. So that property dominates, that property X. So that's the constant V1, V2 over X, and then times the sine of the angle difference between the two locations, delta 1, 2. That's delta 1, 2 is the difference between the voltage phase angle at location 1 and at location 2. So that gives you a power transfer that looks like this sine function. And you can already see that it has a maximum at an angle separation of 90 degrees. If you get anywhere near there or fall over the edge, the lights go out. It's a very bad day. And really, for purposes of keeping the grid stable, you want to maintain phase angle separations in the tens of degrees, somewhere here in this nice, safe, linear range of the curve. And there's a whole field of analysis of figuring out, well, exactly how far can you drive this, because the relationships between synchronous generators at either end gets a little weaker. And we'll come to that. I just want to give you a visual of how the phase angle difference relates to power flow. And this is from a distribution circuit. So we have very small phase angle differences here, something like a degree or a degree and a half. But you can see how that correlates with the solar power that's produced at one end of this distribution feeder. Here's a picture of two generator units to try and get a little bit of that intuition about if the voltage phase angle is more forward, that means the generator is pushing harder. It's facing a stronger reaction. There's physics that is making it push against a stronger magnetic field. And that's a visualization of how we're driving power flow from one power plant to another. So it's where the voltage angle is more positive that we're injecting more power. I'm not going to spend too much time here on the physics of generators, but the point is that there is a feedback system or a feedback mechanism between how far forward the voltage phase angle is and how hard the machine is pushing. So that is what keeps everyone in lockstep. And if we disturb the system, we're going to see an oscillation That's sort of this classic damped harmonic oscillation, which comes out of the swing equation that physics students recognize as a classic dynamic system, a second order differential equation. We're relating the rate of change and the second rate of change, or the acceleration of that voltage phase angle delta. We're relating that to the difference in mechanical power input and the electrical power that's injected into the grid. So this is really the reason that it's been possible to operate electric grids at all. But it was never directly observable until we had PMUs, right? Because you couldn't actually watch the instantaneous position of a generator rotor. So now just a few more pictures of data. This is just a transmission line trip event in the Western system that shows you, PMU reporting a big drop in frequency. And we can see that kind of classic oscillation. So these are types of events for which PMUs have been super valuable, because this is not something that was recognizable in detail if you didn't have data that were much faster than 1 second. You can see the time scale on this graph is, the units are in seconds. And you see generators tripping offline and a transmission line tripping, and then other generators responding. Here's an illustration of a big event of frequency oscillations after a large chunk of generation went offline. And what we're seeing, what's really interesting, is that even though the generator was lost in Southern California, some of the biggest swings are up in Canada. So that illustrates how much physically the whole network is connected. And it's wobbly in part because there's such a big phase angle difference between the two ends, with a lot of power flowing from north to south, that you're seeing these big oscillations. And Kevin can say a lot more about this. We didn't even know that our Western grid had these standard modes of oscillation until we could observe them with PMUs. And this really is what sets the limits for power transmission, more so than the thermal limits. So just quickly wrapping up, what happens if our signal is not a cosine? And I want to thank Harold Kirkham for some of his papers on the subject, and really raising awareness of the fact that, we're all cheerfully making this assumption we're describing a cosine. In the type of event that I just showed you, voltage as a function of time is not exactly a cosine, because frequency is changing, right? So what is a PMU to report? It's not unambiguous. What should be the right answer? If we talked about phase angle differences between two sine waves. If, like on the right, those sine waves don't have the same exact frequency, then what do you report as a phase angle difference? You can compute a phase angle shift between these two sine waves at some place, at some section, at some point in time that you choose, but it won't be universally true for all past and future times, which is implied in a cosine that it's that way for all past and future times. So the sampling window actually becomes important, and which chunk of time are you actually referring to? Here's another good one. What if you have a deformity in this cosine waveform? There's not strictly a magnitude and phase angle shift that would be the correct answer for a PMU to report. So people in the industry are talking about what rules should we agree on for describing this kind of situation? Or is there a way perhaps to capture a goodness of fit measure, as Harold Kirkham has proposed, that sort of gives you a quantitative metric of, well, how is our waveform conforming to the assumption that it was a cosine? Like in the top row here, we have just a plain cosine function. If we allow for the fact that frequency and phase are actually drifting in time, then there's a way to account for all those terms, but we have to agree on what we mean by the frequency here. Is it just the omega? Is it the rate of, which rates of change do we include, and how do we report the rate of change of frequency, which is an important measure for a sort of understanding how dramatic a disturbance event is happening. How exactly are we to define and quantify that? So we do live in interesting times. This is one of my favorite graphs. This is from an event where there was a major transmission line trip, a couple of trip events, and then solar inverters were reading the frequency of the system, and they were reading something like 57 hertz, which is not what others computed, but there's different algorithms for computing frequency. And so the solar inverters did what they were told to do, which is to disconnect. But that led to 1,200 megawatts of solar resource suddenly disconnecting, which was not the intended outcome. So in particular, with variable resources and inverter-based resources, which we have the luxury to program exactly how we want them to behave, there's a whole different field of opportunity to sort of tune them to the needs of the grid that we're understanding with these very precise measurements. So with that, I think I will close and turn it over to Kevin.